Good morning to all. So in the previous lecture, we seen that what is the Jordan canonical form. So today's lecture we see the next point of our syllabus. What is inner product space? Okay, what is inner product space? The unit number 4, inner product space. Okay. So let f be a field of real numbers. Okay, let f be a field of real numbers or complex number. Okay, and V be a vector space over F. Okay, let V be a vector space over F. An inner product on V is a function. We denote like this function as like this. Okay, an inner product on space on V is a function from V cross V into F. Okay, so the output from a field F, okay, which assign to each ordered pair of vectors alpha beta in a scalar inner product of alpha beta. So this is the value which from field F. Okay, in such a way that first condition. What is the first condition? Inner product of alpha plus beta and gamma is equal to alpha gamma. Inner product of alpha gamma plus beta gamma. Okay. So the function from V cross V into F. Okay. The ordered pair input from V cross V. Okay. And output comes from F. Okay. So if these are the four conditions satisfied, then we say that V is the inner product space. Okay. First condition, alpha plus beta, inner product of alpha plus beta and gamma is equal to inner product of alpha gamma plus inner product of beta gamma. Okay. Second condition, inner product of C alpha and beta is equal to where C belongs to F. Okay. And alpha beta comes from V. Okay. Alpha and beta comes from V and C comes from C with any element from F. Okay, is equal to C into inner product of alpha beta. Okay, and these two property, combining these two property, we call as a linearity property. Okay, linearity property. Okay, so the third condition is that, look at here, if alpha beta, inner product of alpha beta is equal to conjugate symmetry. Okay, inner product of alpha beta is equal to inner product of beta alpha bar. Okay, bar means conjugate of that element. Okay, whatever be the element, we take conjugate of that element. Okay, so inner product of alpha beta is equal to inner product of beta alpha conjugate bar. Okay, so the fourth property is inner product of alpha alpha. If two vectors are same, then inner product of that alpha is greater than or equal to 0. Hence, the inner product is non-negative. Okay, and inner product of alpha and alpha always greater than 0 if and only if alpha is not equal to 0. Here, if and only if statement, not if only. Okay, if alpha and alpha, inner product of alpha and alpha is equal to, is greater than 0, then you have alpha must be not equal to 0. Or inner product of alpha and alpha is 0, it implies and implied that alpha is equal to 0 for any alpha, beta, gamma belongs to V and C belongs to F. Hence, if all these four properties are satisfied by V, vector space V over F, then we say that the V is the inner product space with binary with operation with function, with defined function like that. Here the function. The inner product on V is the function. Inner product on V is the function like this. We can denote. Okay. Now look at some examples of inner product space. Okay, look at some examples of inner product space. Okay, let Rn R raised to n be a vector space. Rn R raised to n means what? The element of this R raised to n look like here. If alpha belongs to R raised to n, so there are n coordinates are there. Okay, so R raised to n be a vector space over R, then alpha, which is the element from Rn, we can write alpha is equal to x1, x2 up to xn, and beta is equal to y1, y2, up to y1. These are the two elements from R raised to n, which has n coordinates. Okay, so y1, all the yn, xi and yi comes from R. Okay, so the function, inner product function, this is the inner product function from Rn into Rn cross Rn, sorry, Rn cross Rn to R, where R is the field defined by inner product of alpha beta is equal to summation I is equal to 1 to n xi into yi. Okay, this defines an inner product on Rn. Okay, which is called standard inner product space. Okay, this is the definition of standard inner product space. Okay, this alpha comes from Rn, this Rn, and this beta comes from Rn, and the alpha and beta in the form of x1, x2 up to xn. Why? Because alpha comes from Rn and beta comes from Rn. Okay, so the inner product defined like this. The inner product of alpha and beta is equal to summation I is equal to 1 to n xi into yi. Okay, xi into yi. Now see, one more example is there. If Fn, if Fn for alpha beta belongs to f raised to n Fn, so alpha and beta comes from Fn, then we can write alpha is equal to alpha 1, alpha 2 up to alpha n, and beta is equal to beta 1, beta 2 up to beta n, defined by alpha beta. Inner product of alpha and beta is equal to alpha 1 beta 1 bar, alpha 2 beta 2 bar, plus up to alpha n beta n bar, which is equal to summation I is equal to 1 to n alpha I beta I bar. Okay, Fn, this is the vector space. Okay, over the field F, Fn of F. Okay, this define an inner product on Fn, which is called standard inner product space. Okay, standard inner product space. In the previous example, we taken that here Fn is equal to R, set a real number. Okay, F, the field we taken as set of real number. Okay, this is an definition of inner product space. Okay, if you take F is equal to R, then every number is a real number. So beta bar is equal to beta I bar is equal to beta I, because in the set of real number, A bar is equal to A. Okay, so there is no complex the imaginary part. Okay, in the set of real number, there is no imaginary part is there. Okay, hence in the set of real number, beta I bar is equal to beta I. Hence, in the previous example, we taken as F is equal to Rn. Okay, the next example is that let V over F be the vector space of all continuous complex valued function. Continuous function, all the functions are continuous, and the output is the complex value. Okay, if you take an F from V function, set of the vector, this is the vector space of set of all complex valued function. Na? So the element is like functions, all the elements are like function. Okay, so output comes a complex valued function. Okay, be the vector space of all continuous complex valued function defined on unit interval 0 to 1, where t running from 0 to 1, which means the function, all the functions defined on closed interval. Why closed? Here 0 less equal by t less equal by 1. So all the complex valued function defined on closed interval 0 to 1. Okay, and this collection will be taken in the V vector space. Okay, if f of t and g of t belongs to V, then these are the complex valued continuous function. Then define inner product of these two functions. Inner product of these two functions, f of t and g of t, is equal to integration 0 to 1 f of t into g of t bar. Okay, f of t into g of t bar dt. Okay, we taken the as interval 0 to 1. So lower limit is 0 and upper limit is 1. This defines an inner product on V. Okay, so these are the examples of all standard inner products. Okay, so this defines an inner product on V. Why? Because this inner product, this vector space satisfy all the previous four properties which we have seen in the last page. Okay, on last page we will see we seen that for the fourth condition here this vector space satisfy all that four properties. Hence, this vector space and inner product space. Okay. Now the definition, one more definition is there. An inner product space is a real or complex vector space together with a specified inner product on that space. Okay, what it means? An inner product space is a real or complex vector. If the field is real, then it is real vector space. If the field is complex, then we say that it is complex vector space together with a specified inner product. Together with, we taken as a function inner product na. So together with a specified inner product on that space. Okay, so next definition is that norm or length of a vector. How to calculate norm of a vector or length of a vector from inner product space. Okay, let V be a inner product space. Okay, let V be the be an inner product space, and let alpha belongs to V be the any vector from this vector space, then the norm or length of the vector alpha. So then the norm or length, we can say anything, norm or length of the vector alpha is written like as norm of alpha. This is the symbol of norm. Okay, distance from origin. Okay, what is norm? We have calculated in the previous year, last year. Norm is nothing but length of a vector from origin. Okay, is defined as the positive square root of inner product of alpha, that is positive square root of inner product of alpha, that is norm of alpha is equal to square root of positive square root, means we have taken only positive value, not negative. Okay, because inner product is non-negative. Hence, norm of alpha is equal to square root of alpha, positive square root of inner product of alpha. Okay, this is the definition of norm of a length, norm of a vector or length of a vector. Okay, now the next part is there. What is the next? The theorem is there. Okay, so if in an inner product space V over F, prove that. First, what is the first statement? The inner product of A alpha minus B beta and gamma is equal to A into inner product of alpha gamma minus B into inner product of alpha gamma. Okay, sorry, here is the printing mistake is there. Beta gamma is there. Okay, instead of this alpha, write as B gamma. Sorry, alpha gamma, take here as a beta gamma. Okay, so first condition, what is the inner product of A alpha minus B beta, comma gamma, which is equal to A into inner product of alpha gamma minus B into inner product of beta gamma. Second condition, inner product of alpha and A beta plus B gamma is equal to alpha into inner product of alpha beta plus B into inner product of alpha gamma. Okay, so we have to prove these two statements if given that V is the inner product space. Okay, so first, to prove that, the first statement, A inner product of A alpha minus B beta and gamma is equal to, okay, inner product of A alpha minus B beta, okay, and gamma is equal to A into inner product of alpha beta alpha gamma minus B into inner product of beta gamma. Write A and inner product of alpha gamma minus B into inner product of beta gamma. Okay, consider the left hand side of the above equation. Okay, which is equal to, we can write like this, inner product of A alpha plus into bracket minus beta into beta, small b into beta, and gamma, which is equal to, by linearity property of inner product space, we can write A into inner product of alpha gamma plus minus beta, which is from F. This A and B comes from field F now. So we can write inner product of beta gamma by which property? By linearity property of inner product space. Here they given as a V is the inner product space. Hence the V over F satisfy all the four properties of inner product space. Okay, which is equal to A alpha into gamma, A inner product of alpha gamma minus plus minus minus B into beta gamma, inner product of beta gamma. Okay, this is the first statement. Now, to prove the second statement, to prove inner product of alpha A beta plus B gamma, which is equal to A bar into inner product of alpha beta plus B bar into inner product of alpha gamma. Okay, here alpha and gamma is there. Okay, but here beta and gamma. Why? Because here look at A beta alpha beta plus alpha gamma is there. Na? So take the right hand side, left hand side of the above equation. Inner product of alpha A beta plus B gamma, which is equal to, by conjugate property of inner product space, we can write inner product of A beta plus B gamma and alpha bar, okay, by conjugate property of inner product space. Hence, which is equal to, take A to the outside of inner product space and B also outside to the inner product space. By linearity property, we can write like this: A into inner product of beta gamma, beta and gamma, plus B taken as the outside and inner product of alpha, sorry, gamma alpha. Okay, and whole bars is there. Okay, by which property? Linearity property of inner product space. Okay, so give the bar separately to both. Okay, so is equal to A into beta inner product of beta alpha bar plus B into inner product of alpha gamma alpha bar. Okay, we can write A plus B whole bar is equal to A bar plus B bar. We know that. Okay, so which is equal to A bar into inner product of B alpha bar plus beta alpha bar plus beta bar into inner product of gamma alpha bar. Okay. A into B whole bar is equal to A bar into B bar. By this property, we can write like this. Okay. But beta alpha bar is equal to inner product of beta alpha bar is equal to inner product of alpha beta. And inner product of gamma alpha bar is equal to alpha gamma. Okay. And A bar and B bar as it is. Okay. In the next, hence, this is the proof of the above theorem. This is the proof of the above theorem. Now, the second theorem. Okay. Second theorem. Let V be an inner product space, then for any alpha beta and gamma belongs to V and C belongs to F, then the following statements are true. Okay, we have to prove all these five statements are true when V is the inner product space on V. Okay, what is the first? Inner product of alpha in alpha beta plus gamma is equal to inner product of alpha beta plus inner product of alpha gamma. Okay. Second statement. Inner product of alpha and C beta is equal to C bar. If C is here, then only C comes outside this inner product space, inner product. Okay. If C is at the right side of the element, right side of the inner product, then it comes as a C bar. Okay. Note it is. Note that. Okay. So if inner product of alpha C beta is equal to C bar, this is important. C bar into inner product of alpha beta. Inner product of alpha and 0 is equal to 0, which is equal to inner product of alpha and 0 and alpha. Both zeros and alphas belongs to V. Okay, the fourth statement is inner product of alpha and alpha is equal to 0 is implied that alpha is equal to 0. And fifth statement is there, if alpha and beta, inner product of alpha and beta is equal to inner product of alpha and gamma for all alpha. This is the important, for all alpha belongs to V. And if it is true for all alpha belongs to V, then beta is equal to gamma. These both the element are same element, not a different. For all alpha belongs to V. If this statement holds, then beta is equal to gamma. Okay. Now to prove the first statement, look at here. How we can write by conjugate property this inner product of alpha and beta plus gamma, which is equal to beta plus gamma and alpha bar, inner product of beta plus gamma plus alpha and alpha bar by conjugate property of inner product space. Now, okay, by linearity property, we can write like this: inner product of beta alpha plus inner product of alpha gamma. Give write like separate, likewise separate. Okay, like write separately. Okay, so beta plus beta alpha, inner product of beta alpha plus inner product of alpha gamma bar, which is equal to inner product of by conjugate property. Okay, conjugate property. If A plus B, inner product of beta alpha bar plus inner product of gamma alpha bar. If A plus B bar whole bar is equal to A bar plus B bar. Okay. Then by conjugate property, we can write like this. Beta alpha bar is nothing but alpha beta, and inner product of alpha beta gamma alpha bar is equal to inner product of alpha gamma. Hence, the first statement holds. Now, the second property. What we have second, if alpha C beta, inner product of alpha C beta is equal to, by conjugate property, C beta alpha bar, inner product of C beta alpha bar. Okay. which is equal to by linearity property. Okay, by sorry, linearity property is there, not conjugate property. This is by conjugate property, but by linearity property, C outside the inner product. So C into inner product of beta alpha bar whole bar, then write this conjugate separately, which is equal to C bar into inner product of beta alpha bar. Okay, by linearity property. Okay, if you have A into B bracket whole bar, then we can write A bar into B bar. By this property, we can write C bar into B alpha bar, inner product of B alpha bar. Conjugate property B alpha bar means alpha beta. Sorry, beta alpha bar, inner product of beta alpha bar, which is equal to inner product of alpha beta by conjugate property, and C bar as it is. And the second statement holds if C is the right side of the inner product. Okay, then it comes outside as a bar, C bar. Okay, now the third property. Third property. Wait a minute. Consider alpha 0, inner product of alpha 0 is equal to inner product of alpha 0 into 0. Okay, where 0 is the 0 vector of V. Okay, not a field, it is the element of V. Okay, now by conjugate property we can write like this: inner product of 0 into 0 alpha bar. Okay, if 0 is here, then we can write taken outside 0. Okay, then 0 into 0 alpha bar, inner product of 0 alpha bar by linearity property. Okay, hence 0 into anything, it becomes 0. Hence alpha into 0, inner product of alpha 0 is equal to 0. Hence the third statement also correct. Similarly, we can write which is equal to 0 into alpha, 0 alpha, sorry, inner product of 0 alpha. This is the third statement. Okay, now the fourth statement. Fourth, alpha alpha is equal to 0. Inner product of alpha alpha is equal to 0. But by definition of inner product, alpha is equal to 0. Okay, by fourth property. Okay, V is the inner product space. Hence, alpha is alpha alpha. Inner product of alpha alpha is 0 is equal to, by the definition of IPS, inner product space. Okay, IPS means inner product space. Alpha must be 0 by fourth property of IPS. Conversely, let alpha is equal to 0, then consider alpha alpha, inner product of alpha alpha, which is equal to inner product of 0 and 0, which is nothing but 0 from previous statement, from 3. Okay, hence if alpha alpha, inner product of alpha alpha is equal to 0, implies and implied that alpha is equal to 0. Okay, now the fifth condition, fifth statement. Let alpha beta is equal to inner product of alpha beta is equal to inner product of alpha gamma. It holds for all alpha belongs to F. If this statement, let this statement holds for all alpha belongs to F, then the right hand side taken towards left hand side, then it becomes minus. So inner product of alpha beta minus inner product of alpha gamma, which is equal to 0. These are the fields now. The output of the vector inner product space. In an inner product space is the function v cross v2 f now. This is the function v cross v2 f. So this is the vector from field. This is the element from field f. Okay. So we can write like this: by linearity property, inner product of alpha beta minus gamma, which is equal to 0 for all alpha belongs to V by linearity property. Hence, we can write beta minus gamma is equal to 0 by statement number 4. Okay, by statement above 4. If beta minus gamma is equal to 0, alpha beta minus gamma is equal to 0, then beta minus gamma is equal to 0 by statement number 4. Hence, beta is equal to gamma. Understood? Hence, beta is equal to gamma. This is the proof of the above theorem. All the five statement holds if V over F is an inner product space. Okay. Now, the next part is let V over V is equal to Fn, and suppose V is equal to Fn, and suppose and the standard inner product defined on Fn, that is how we can write inner product of alpha and beta. This is the standard inner product space. Summation I is equal to 1 to n alpha I into beta I. Okay. Alpha I into beta I bar. Inner product of alpha and beta is equal to summation I is equal to 1 to n alpha I into beta I bar, where alpha and beta belongs to V, which is in the form of alpha 1, alpha 2 up to alpha n, and beta is equal to beta 1, beta 2 up to beta n. Why? Because alpha and beta belongs to V, which is equal to Fn. N coordinates are there. Okay. Then this the norm of a length, norm of a vector or length of the vector we define like this. Norm of alpha is equal to, we saw the definition of norm. It is the positive square root of inner product of alpha alpha. Okay, the positive square root of inner product of alpha alpha. Okay, by the definition of this inner product, we can write in place of beta alpha bar. Okay, so which is equal to positive square root of I is equal to 1 to n alpha I into alpha I bar. Okay, so you know that if a into a bar is equal to mod a square, you know that if a into a bar, z, if z is the any complex number, then you can write z into z bar is equal to mod z square. Okay, hence by the definition of that, norm of alpha or length of alpha is equal to positive square root of I is equal to 1 mod alpha I square. Okay, hence this is the Euclidean definition of length. Okay, Euclidean definition of length. Why Euclidean definition? Because here we taken f is equal to Fn. Okay, Fn, n coordinates are there. Okay, take n is equal to 2. And in place of f, if we taken as n is equal to 2 and f is equal to r, set of real number, then f2 becomes r2 na. Plane, na, plane. R2 is nothing but plane. But in the definition of, by the definition of norm, it becomes square root of ai square alpha 1 square plus alpha 2 square. If n is equal to 2, then any vector, the length of the vector we define like positive square root of a1 square plus a2 square. So or alpha 1 square plus alpha 2 square. This is the definition of a norm of a length in a plane. Na? Hence, this definition is called as Euclidean definition of length. Understood? Now, the next theorem. The next theorem. Let V be the let V be an inner product space over F. Then for all alpha beta belongs to V and C belongs to F, following statements are true. Alpha is equal to 0. Norm of alpha is equal to 0 if and only if alpha is equal to 0. In any case, okay? In any case, norm of alpha is always greater than or equal to 0. It means that the length of the vector never be negative. It is always non-negative. Okay. So what it means, if the length of the vector is a 0, then it implies and implied if and only if that vector must be a 0 vector of that vector space, inner product space. Okay. So second statement is there. If norm of C alpha is equal to mod of C into norm of alpha. We taken C as a positive value. Mod means mod alpha, mod C is always positive. Okay. Now, to prove these two statements, let V be an inner product space. Okay, let V be an inner product space. Now, to prove that, norm of alpha is equal to 0 if and only if alpha square. Norm alpha square also 0. Okay. If norm of alpha 0 is equal to 0, we have to prove this statement. Okay. Then we have to prove first statement. We have to prove alpha is equal to 0. Taken this and we have to prove alpha is equal to 0. So assume norm of alpha is equal to 0. It implies and implied also a norm of alpha square is equal to 0. But norm of alpha square is nothing but if and only if inner product of alpha is equal to 0. Inner product of alpha is equal to 0. But V is the inner product space. Hence, by the definition of IPS, inner product space, it must be 0. Alpha must be 0. Hence, the norm of alpha is equal to 0 if and only if alpha is equal to 0. Now, to prove that norm of alpha is non-negative, that is, norm of alpha is greater than or equal to 0. Okay. Since norm of alpha is equal to 0, which is equal to positive square root of alpha by the definition of norm. Okay. Positive square root of alpha inner product of alpha, which implies norm of alpha square is equal to inner product of alpha. But by the definition of inner product space, okay, inner product always non-negative, which means it is equal to greater than or equal to 0 by the definition of IPS. Hence, it implies norm of alpha square is equal to greater than or equal to 0. Hence, taking square root from both sides, norm of alpha is always greater than or equal to 0. Okay, this is the first statement of our theorem. Now, we have to prove the second condition, second statement. If alpha belongs to V, if alpha belongs to V and C belongs to F, C be the any vector, sorry, C be a any element from the field F and alpha be a any vector from V. Now, to prove that norm of C alpha is equal to mod C into norm of alpha. Okay, we know that the definition of norm of V. Norm of alpha is equal to positive square root of inner product of alpha. Hence, by this definition, we can write norm of C alpha is equal to positive square root of inner product of C alpha into C alpha. Okay. So, taking square on both sides, we get norm of C alpha square is equal to inner product of C alpha. Okay. By the definition of linearity property, which is equal to if this is the C comes to outside the inner product, C into alpha C alpha. And now this C comes outside the inner products, which is C. Now we have to this C. Okay. This is the C comes outside the inner product by taking C bar. Okay. So norm of C alpha square is equal to, this is the C as it is, and this is C, this C comes toward outside the inner product taking C bar. So C into C bar of inner product of alpha. Now we know that if Z is the complex number, Z into Z bar is equal to mod Z square. By that definition, the norm of C alpha square is equal to C into C bar means mod C square and alpha norm of alpha square. Okay. Hence, taking the square root of this is the square, this is the square, and also this is the square. Now the taking the square root on both sides, the norm of C alpha is equal to mod C into norm of alpha. Okay, this is the proof. Okay, now the next definition is, next theorem is Scots inequality. Okay, and triangle inequality. The next definition is Scots inequality and triangle inequality. Now we see what is the Scots inequality. Okay, in an inner product space, we have to prove that mod of inner product of alpha beta is less than or equal to norm of alpha into norm of beta for any alpha beta belongs to V, which is the inner product space. Okay, we have to prove this condition, and this inequality is nothing but Scots inequality. This is the equality is also called as Scots inequality. Okay, what is norm of mod of alpha beta, inner product of alpha beta, which is less than or equal to norm of alpha into norm of beta. Let's see a proof. If alpha is equal to 0, take alpha is equal to 0, then norm alpha is equal to 0. And also inner product of alpha beta is equal to 0 into beta. The inner product of 0 beta is equal to 0. Okay, by the definition of IPS. Hence, and norm of alpha is equal to 0. If we take an alpha 0, norm alpha is also 0. Hence, it implies mod of alpha beta is equal to 0 and norm of alpha into norm of beta is equal to 0 into norm of beta which is equal to 0. Hence, there is nothing to prove in the statement if alpha is equal to 0. Therefore, this inequality in this case holds. The Scots inequality holds if alpha is equal to 0. Let us assume that alpha is not equal to 0. Any non-zero vector belongs to V. Okay. Then norm of alpha is also not equal to 0. Okay. Then norm of alpha is also not equal to 0. That is, norm of alpha is a positive value. Okay. Also, 1 upon norm of alpha is also real number. Okay. Let gamma, we define gamma like this. Beta minus inner product of beta alpha upon norm alpha square into gamma into alpha. Okay, this is the, we define a new vector gamma like this. Okay, why we are defining like this? We have to prove that this Scots inequality. Okay, so define the gamma vector like this: beta minus inner product of beta gamma upon norm alpha square into alpha. Okay, so by the definition of inner product space, we have gamma gamma, inner product of gamma and gamma greater than or equal to 0. Okay, any vector which is not equal to 0, then inner product always not greater than or equal to 0. Okay, write the uh, write the gamma vector here. Okay, right, what is the gamma? Beta minus inner product of beta alpha alpha square normal alpha square upon into alpha comma beta minus inner product of beta alpha into alpha upon normal alpha square, which is always greater than equal to 0 by the definition of inner product space. We are writing only the value of gamma here. Okay, nothing much. Okay, so by the linearity property of inner product space, we write beta here and this vector beta minus beta alpha, inner product of beta alpha into alpha upon a normal alpha square like this, and this minus term here, this is the scalar value. Okay, this is the scalar value, not a vector. Okay, into what is the scalar? Inner product of beta alpha upon alpha square into inner product of alpha Okay, inner product of alpha and beta. This is the alpha is present here. Okay, then this also, this whole vector comes as it is. Okay, beta minus beta alpha into alpha, inner product of beta alpha into alpha upon norm alpha square, which is always greater than or equal to 0. Understood? We return, we write by linearity property. Okay, this beta here and this whole scalar, this is the scalar here and this alpha here and this vector as it is by linearity property. Okay, also apply linearity property to this vector. Okay, beta beta here, inner product of beta and beta minus, this is the scalar value. Okay, here beta alpha bar. Okay, why bar? Because in the beta alpha to the right side of inner product, in the inner product. Okay, so it comes outside with bar. Okay, so inner product of beta alpha bar upon norm alpha square, and this is the beta and alpha here. Okay, inner product of beta alpha minus. Okay, this is the beta alpha norm alpha square as it is, and this is the, by linearity property we can write like this: alpha beta here, inner product of alpha beta plus, okay, minus, and this minus becomes plus, and beta alpha into norm of alpha here, and this is beta alpha into norm upon the norm of alpha here. Okay, this term is here and this is the term here, and alpha into alpha here, which is greater than or equal to 0. This is the only calculative part. We have to solve all these mathematical part. Okay, and local लावायचं काहीच नाहीये करायचं. So inner product of beta beta is equal to norm of beta square by the definition of norm. Okay, this positive value, okay, this is the positive value and this is the negative value, cancels. Okay, this alpha alpha is nothing but norm of alpha square. Okay, this norm of alpha and this of norm of alpha get cancelled. Okay, this is the norm of alpha and norm of alpha get cancelled, and remaining this part cancel with this part. Okay, beta alpha bar beta alpha upon norm of alpha square. The sum here negative term, here positive term. This alpha, this with the negative sign can here get cancelled. Okay, so the remaining part is there, norm of beta square minus this part, inner product of beta alpha into inner product of alpha beta upon norm of alpha square, which is greater than or equal to 0. Okay, similarly here. Okay, norm of beta square minus alpha beta bar. Write this beta alpha as beta alpha bar and alpha alpha beta bar, and this is the alpha beta inner product of alpha beta upon alpha square, which is greater than norm of alpha square, which is greater than equal to 0. Okay, again this write like as it is, and take this term whole terms to the right side, and if this is the z and this is the, this is z and this is the z bar, z into z bar mod z square, by this property you can write like this: norm of alpha beta square, whole term as it is, taken to the right side. Now here the denominator alpha norm alpha is in the denominator place, takes towards the left side, then it implies alpha square into beta square, alpha norm of alpha square into norm of beta square, which is greater than or equal to inner product of, in the mod, inner product of alpha beta square. Now by taking the square root of both sides we get alpha beta, sorry, norm of alpha into norm of beta is greater than or equal to mod of inner product of alpha beta. Okay, this is the proof of Scots inequality. Okay, so in the next lecture we will see what is the triangular inequality and Gram-Schmidt orthogonalization process. Okay. So today we see that what is the Scots inequality, what is the inner product space, and some theorems. Okay. Thank you.